This is more normal distribution, and all of the bets that are made in statistics that we're concerned with come from the normal distribution. So all of this stuff is what we're betting on and how it comes about. And there's only two things for the normal distribution that you need in Excel. It's NORM.DIST and NORM.INV. The NORM.INV is the backwards version of NORM.DIST. So NORM.DIST, you put in a number, and NORM.DIST gives you the area to the left of that number, what the probability is up to that point. NORM.INV, you put in a probability, and it gives you the value that cuts off that amount of area to the left. If I want 30% cut off to the left, right, and I keep saying to the left because that's the way they work. Minus infinity up to a 30% mark, we get the value that's cut off. So this is equals norm.inv, and you put in 0.3, and we need a mean and a standard deviation. I'll use 100 for the mean, the average, and 20 for the standard deviation. So that value is 89.5. That's the number that cuts off 30% to the left. If I want the value to the right, that's 70%, and the way I would have to get it is to use the 0.3. 0.3 to the left gives me 0.7 to the right. So that the second one on there is 0.7 to the right, it's 89.5. The only command is always from the left, and the normal goes to plus infinity and minus infinity in these tails. And the only thing about it is that the probability of being that far out is so low that we can ignore it. But it literally does not end anywhere. If I want 30% to the right, I want 0.3 that way. What do I have to put in? 0.7 equals norm.inv .INV 0.7. Everything has to come from the left. And that's 110. So 110 cuts off 70% to the left and 30% to the right. One thing that's important that I need mostly, I don't need one end or the other. Mostly for bets in statistics, what we need is the middle. We don't care about the ends. We want what's in the middle. So we have an upper limit and a lower limit. And this is the only notation in statistics that makes any sense. Lower limit and upper limit. 80%. 80% in the middle, and I need the numbers that cut off 80%. I need what cuts off this tail and this tail. 0.1. It's 0.2 outside altogether and 0.1 in each tail. Right, there's two ways to do this. One is I can get the 0.1 if I use the norm.inv equals norm.INV NORM.INV, and I want 0.1, and I'll use the 120 again. Oh, got that one wrong. 0.1. 0.1. That value is 74.4. That cuts off 10%. If I want the upper end, I need to use 0.9 because I want 10% to the right, 0.9 to the left. And that's going to cut off the middle 80%. Equals NORM.INV 0.9. 100, 20, and that's 125.6. That cuts off 80% in the middle. The bets and statistics are basically symmetric. So that I want to know what's the chance that it's less than 74 and greater than 125, or the probability that it's between those two things. The other way I can do this, using either one of these two, 100 is in the middle, and this is measured in standard deviations, so that the distance from here to there is the same number of standard deviations as it is from here to here. So if I subtract this 74.4 from 100, I get 100, or I get 25.6. I add 25.6 to the 100, and I get the other end. All right, it's always symmetric. All the bets in statistics are symmetric. The normal distribution is symmetric, so that's the way it goes. All right, try 95% in the middle. This is a very common bet. I want to know what cuts off 95% in the middle, the lower end and the upper end. So here's 95%. And if you draw a picture, you will never go wrong. 95% in there. How much is in the left tail and how much is in the right tail? 5% total, half in each one. Two ways to get it. What's the first one? What's the low end? What probability do I use for the low end? Everything comes from the left. 0.25. 0.025, yeah, 2.5%. And the good thing is if you get it wrong, it's pretty obvious. Equals NORM.INV 0.025. 100, 20. That's 60.8. And if you remember the empirical rule, 2 standard deviations down, 2 standard deviations up. This is 100 in the middle, 80 and 60, 120, 140, and by the empirical rule, that's 95%. So the empirical rule is almost exact. for this end, what probability do I have to put in here to get the upper end? 2.5%, 95%, 0.975. 2.5 plus 95 cuts off that 0.975. Equals NORM.INV 0.975. And that's 139.2. Which is the upper end on the 95%, so it's about 140. Last one, what is 60%? What do I look up to cut off 60%? And these are never drawn to scale. What's to the left? What's to the right? What probability do I have to look up to find the value that cuts off 60% in the middle? How much is outside altogether, and how much is half of that? So here I need 0.2, and this one I would need 0.8. And that would give me the cutoffs. Right. This is all the same all the time. What's in the middle? What's to one end? What's to the other? It's symmetric. So it's 60, 0.2 here, 0.8 there, cuts off 0.2 to the right. 80% to the left, 0.2 to the right. As straightforward as it can ever be. Always draw a picture. And if you draw a picture and label it and put on the empirical rule, 2 up, 2 down, 1 up, 1 down, you can't go wrong. And if it's wrong, if you get an answer that looks wrong, it is wrong. Try and estimate what you're going to deal with. Like this one, 60%. This would be 100. If I go to 120, what's between 120 and 80? 1 up, 1 down, symmetric. That's 68%, so that the lower limit here has got to be a little bigger than 80, and the upper limit has got to be a little bit less than 120. Drawn to scale, it looks better like this. 80, 120, so that this number has to be a little bit bigger than 80, and this one has to be a little bit smaller than 120. And always go back to the empirical rule and cut off the chunks that you know about, 95%, 68%, and compare it to what you're looking for. So you can estimate these things pretty easily. And I said this one's bigger than 80. Why not? 20% to the left equals NORM.INV 0.2 to the left, 100, 20, and it's 83.2, which is a little bigger than 80. That's the NORM.INV. Area always to the left, and you have to figure out what it is that you want from that. That's the normal distribution. We have another version of the normal. And this is the standard normal distribution. The distribution we had before, it's written as normal, 120, average, and standard deviation. The standard normal distribution has a mean or an average of 0 and a standard deviation of 1. The reason we have a standard normal distribution is because the guys who invented this didn't have a computer. In Excel, if I want a mean of 100, standard deviation of 20, I just put it in there. There was no standard. Every table I would make would have to be different. If I had a standard deviation of 19 instead of a standard deviation of 20, with the same average, I would need a new table because I had to use a table. What they did was standardize everything. So standard normal is always measured in z-scores. What's the distance from the average measured in standard deviations? So I have an x minus an average divided by the standard deviation. So if I have 60, that's the low end of the 95% minus the average. I divide it by the standard deviations. And that's 2 standard deviations below the average. The standard normal is always measured in standard deviations. And this is where the empirical rule comes from. 2 standard deviations down, 1 standard deviation up, or 2 standard deviations up is 95%. 1 down, 1 up, and this is a standard normal table. I think I got one here. And this is history. This is a standard normal distribution table, and this is the way it had to be done before. I didn't have a table for every possible mean and standard deviation. So I've got one that has a mean of 0 and a standard deviation of 1. And if you look at the table, on the left is the z-score, number of standard deviations. Across the top are the decimals in there. So if I go to -2 here and go over, this is 2.0 minus 2.1 minus 2.01 minus 2.02 and so forth. So this is what Excel replaces. So to have this work, if I wanted 60, I would get the z-score and then look it up in the standard normal table, because that was the only way I could do it. So instead of 60, I would look up -2 in the standard normal table, 2 standard deviations down. If I wanted 80, this is equal to -1. I would look up -1 in the standard normal distribution. We don't have to use the standard normal, but it is so deeply embedded in statistics and in math and in general stuff that it's stuck there. But that's how deeply the standard normal is stuck into everything we got. So that to use it, I have to take whatever I've got, convert it to z-scores. How many standard deviations? I look it up in the standard normal table, and then I can convert it back so that anything I do with the standard normal, I can do with the normal distribution function, NORM.DIST, because it adjusts for the mean and standard deviation. The NORM.S.DIST is the standard normal. And I would use it just like before, except for 2, minus 2, that's a 60 on my 100 average 20 scale, NORM.S.DIST. And it helps if you actually use a 0 there. In this list, there's the NORM.DIST, the first command, NORM.INV, and then NORM.S.DIST and NORM.S.INV. They are the equivalent with a mean of 0, standard deviation of 1, measured in standard deviations. So for 90 is the example. Instead of a 90 with 100 and a standard deviation of 20, I have to get the distance from the average in standard deviations. So how far is 90 from 100? You get minus 10. It's 10 below the average. I divide it by 20, and I get minus 0.5. So 90 is 1/2 of a standard deviation below the average. So if I put in here NORM.S.DIST minus 0.5, and it assumes that you're using 0 and 1, so it's only a cumulative. It's always cumulative, but you don't put in a mean or a standard deviation. Always use cumulative when you're using the normal. 90 cuts off 0.31%, 31% to the left. If I go to NORM.DIST, (90, 100, 20, and cumulative, I get exactly the same answer. If I wanted to do this with standard normal, I just use that command, but I need the distance in standard deviations. Now I can go back, and this is the fundamental theorem of statistics. Everybody's got a fundamental theorem, like the fundamental theorem of algebra and the fundamental theorem of calculus. I don't know who decided those things, but the fundamental theorem of statistics is Z, the distance from the average measured in standard deviations, is that I can go back. X is equal to the average plus the z-score times the standard deviation. So if I want to know what cuts off 40% to the left, in here I use equals NORM.S.INV, 0.4 to the left, and there's nothing in here except probability, and I get minus 2.5. If I want to know what that is on the elephant weight scale, I have to convert that minus 2.5 to my 100 and standard deviation 20, so that it becomes minus 2.5. 100 plus, and the score is minus 2.5 or minus 0.25 times 20, which is 100 minus 5, which is equal to 95. The equivalent of minus 2.5 on the 120 scale is 95. And if you go back and I put in equals NORM.INV 0.4 to the left, 100, comma, and 20, comma, cumulative. Nope, not cumulative. It's already cumulative. I get 94.9. All right. See the deal here? There's nothing here new or different. If you draw a picture, it will always come out right. So this is the basis for bets in statistics. You're flipping coins with someone, heads or tails, and they get 2 heads in a row. Do you suspect the coin is fake or bad? 3 heads in a row. 4, 5, 100. Yeah, you're not sure what's going on. How about 90 in a row? 80, 10 in a row. 20? Somewhere in here we got to have a cutoff. At some point you say, this is unlikely. In this stuff, unlikely usually means in the tails at 2.5%. This is called an alpha level. And almost inevitably, alpha is equal to 0.05. And this is, you select this. Most people will cut off at 0.05 on either end. So if I'm flipping coins, I find the equivalent of +2 on the upper end, or if I'm doing tails, on the lower end. And I say that whatever number this is on my real scale, mean standard deviation, if it's bigger than 2, I don't believe it anymore. If it's less than -2, I don't believe it anymore. You have to have a cutoff somewhere, and that is the usual cutoff.